Welcome to the Machine Learning Unplugged episode 2. These are shows where the conversations are much more off the cuff and we don't do any preparation in advance. Well, to be honest, it's against my religion not to do any preparation, but relatively speaking, we don't do as much preparation. We hope that this will create a casual yet dynamic dialogue with a different stylistic flair than our formal street talk. Now, I'm Tim Scarfe, and we also have Keith Duggar and Walid Saba as co-interviewers. They almost need no introduction for fans of MLST. Keith, of course, got his Ph.D. from MIT, and Walid is the consummate polymath and is extremely well known for shitposting on LinkedIn about what he perceives to be the deep learning runaway train. Now, today we're going to be bringing Walid's linguistics nous to help us co-interview our guest. So on that subject, Dr. Guy Emerson is our guest today. Guy is a computational linguist and obtained his Ph.D. from Cambridge University, where he's now a research fellow and lecturer. He models human language, implements those models computationally, and then tests them using real-world data. Guy is also an aficionado of ballroom and Latin dancing, which we'll let him get away with. Guy, it's an absolute honor to have you on the podcast. I was just reading your PhD thesis, and your opening line was that your thesis was all about meaning, how to represent it, how to learn it. You said that you wanted to shed light on what it means to know a language and to push forward the limits of machine learning. So from a machine learning point of view, a learning algorithm requires that, requires an objective, right? So in the case of language, what should that objective be? And you argued that it should learn semantic representations that are generally useful rather than tied to a specific task. You argued that linguistics clarifies the goal and machine learning provides the tools. The aim of distributional semantics is to design computational techniques that can automatically learn the meanings of words from a body of text. The twin challenges are, how do we represent meaning and how do we learn those representations? We want to learn the meanings of words from a corpus, exploiting the fact that the context of a word tells us something about its meaning. This is known as the distributional hypothesis. It's an idea which you said had its roots in American structuralism and British lexicology, although we will debate whether the company of words means statistical co-occurrence or logical and type constraints. Many will know the quote often cited from Firth, which is that you know a word well by the company it keeps. And most work on distributional semantics learns a vector space model where the meaning of each word is represented as a point in a high-dimensional vector space. You argued in your 2018 PhD thesis that vector space models cannot capture various aspects of meaning, such as polysemy, which is a Greek word meaning of many senses. So, for example, the word get might mean understand or procure or become. Anyway, it's amazing to have you on the show, Guy. I mean, why don't you start by saying hello and expanding a bit on your thesis? Because you presented a distributional model which can learn truth-conditional semantics. Can you tell us a bit about it?
Yeah. Well, the thought, actually, I could just follow up on one point that you mentioned when you said people usually cite Harris and Firth about distributional semantics. Because I think actually most people who cite them haven't actually read those papers that they're citing. If you go and read Firth, and I did because I thought I actually want to know what did he actually say about meaning. He spends a long time analyzing poetry, actually, which is probably not what people are thinking of now. If you're training, a huge language model, they're not thinking, oh, can we do a better analysis of a particular poet's body of work? But that's something that Firth was interested in. So I think people, took those ideas as inspiration in terms of modern distributional semantics. In my work, what I was trying to do, and what I'm still doing, because I'm still building on that work that I did for my PhD, is to have a truth-conditional approach to distributional semantics. So not just learning vectors. If you really think about why do we want to learn vectors for everything, and if you look at, modern deep learning, you put everything as a vector, right? And there are good computational reasons for that in terms of vectors being well-defined, computationally convenient. But if you really want to model meaning, is a vector the right thing to use? And so in my work, I'm trying to look at a different approach where we can look at meaning in terms of truth. So we can say, when is a word or a sentence true and what is it true of? And characterize meaning in that way. And then to do it in a distributional way. So rather than trying to sit down and, write down a theory by hand, actually learn that theory from data, which is really a big challenge. And I think that's a challenge which more traditional linguists have not looked at in as much detail. And I think sometimes underestimate the difficulty of actually trying to pin down, what meaning really is when you think about how you can actually learn it from actual data. And so trying to connect those two sides together. So the formal truth-conditional aspect of semantics with the data-driven distributional approach.
Maybe you could talk a little bit about, because and I'm going to kind of play devil's advocate here. Somebody could say, look, hey, my numerical vectors are really probably more appropriately arrays, and I loved how in your thesis you spent some time to talk about that kind of confusing terminology, the difference between vectors in computer science versus vectors algebraically, etc. So kudos to that. But somebody could say, hey, look, my arrays, they're just real numbers. If the machine learning algorithm finds it useful to work with probabilities, they could easily be probabilities. So in what sense?
Oh, yeah, I mean, my model is also probabilistic. So on that level, I definitely agree that, I'm not getting completely away from using vectors, using probabilities in my work. I mean, if you look at the details of the model, you can find vectors.
Right.
But the difference is, what is the high level structure of the model? So rather than just saying, okay, we've got vectors in, vectors out, we're going to, fit the data, but then actually, what are we trying to learn? So what I'm trying to do is to have a model where we have that high level structure, which we can interpret in a linguistic way, but then leave the details to the machine learning algorithms.
Yeah, and that's what I wanted you to mention there. So really, when you say, it's about these, truth or these truth conditional functions, what you're saying is that on top of the normal vectors, and I'm going to use that word, loosely the way most people, on top of the normal vectors, you're imposing some additional structure, some additional constraints, namely the laws of probability theory and some compositional rules for how to go from truth functionals on words to truth functionals on higher structures, sentences, phrases, etc. Is that right?
I'm hesitant to say truth functional on words because what I'm not doing is saying that the input is a sentence and then an output is, truth or something else like that. And I think a lot of, for example, if you look at large language models and that approach to language, everything's in terms of language, right? You've got words that you've observed, you're predicting the next word. Mm-hmm. Everything's in terms of words. In my work, I'm saying that we need to have this distinction between the words and the objects that the words are describing.
Okay.
And of course, if you think that I'm doing distributional semantics, this immediately seems tricky, right? Because we don't actually observe the objects, right? We just observe words. So in doing distributional semantics, it becomes quite tricky because the actual entities are all latent. You don't observe those. So it becomes a computational challenge to actually build a model that, that can do that at all.
Right.
But by having that structure, which is, it's a very high level structure in terms of the model, because the details of what actually are we using to represent an entity, how are we actually representing the meaning of a word, the details of that, you have to go into the parameters of the model. But the high level structure is in terms of this relationship between words, entities, and truth.
Can I say, Guy, that your main concern is that there aren't so many operations you can do on vectors, right? Is that really the inspiration of this, that you need a richer object?
Yeah, that's one way you can put it. The vectors don't really have the kind of structure that we would want to talk about lots of logical concepts and compositional concepts. They just don't. You don't have corresponding operations in a vector space.
So, for example, we know in language we need to do conjunction and negation and all that stuff. While all I can do with vectors is similarity. I mean, the main. While language composition is more complex, that's the inspiration. Right. Okay.
Yeah.
But the thesis is still the same in that words get their meaning from co-occurrence, from data. You still share that with the traditional, right?
Well, I would say that you can't get 100% of the meaning purely from text. You do need to have some kind of grounded context as well. So, a purely distributional model is not going to give a complete semantic model because you do need to somehow get that connection to the real world,
to the word, and this is where truth comes in the traditional truth conditional semantics, like something has a meaning if I really understand how the word is.
Well,
Yeah.
Right.
can we leave aside grounding for a little bit, because I definitely want to get into grounding with you a bit later, but I think we can stay within the context that Walid brought up, which is, so the distributional learning on text, do you still believe that it's the case that everything that can be learned from the text, so forget about other grounding material, but everything that can be learned from the text can be learned by co-occurrence, or are there even longer range, or less statistical relationships that are going to be missed?
Well, I guess it depends a bit on how you're defining co-occurrence. If you just mean co-occurrence in a word window, then I would say no, that's not going to be enough, because you do have, longer distance connections within a text.
Right.
Even within one sentence, right? You can have long distance dependencies. Within a document, you're going to have, relationships within the text that are maybe less formalized, but as, are still there. That latter part, I haven't even begun to put that in my model. I'm just looking, within one sentence in terms of what I've actually implemented in my work. But, I'm aware of that bigger picture, that even looking at the, syntactic and semantic relations within a sentence is not going to be the complete picture in terms of what you could learn from text.
Okay.
No matter how large the corpus.
So when it comes to the size of the text, I think here is an area where you can see a difference in research goals between different researchers. So, you see these huge language models being trained now, which are trained on such enormous corpora that it's orders of magnitude larger than a human's experience in their whole lifetime in terms of the amount of language data.
Oh, much more.
Right, it's orders of magnitude more. And so from the point of view of trying to model human language, you could say, well, actually, these huge language models just are not realistic. They're not going to be able to tell us something about how humans learn language, because no human is going to learn from 1,000 lifetimes of data, right? So, whether we want to learn models using that size of corpus, that really depends on what your research goals are. And for me, I'm not interested in training these supermassive language models, because that is not going to tell me something about human language learning.
Well, so maybe since we talked about grounding, I guess we can go ahead and jump into that. And so just let me try and set this up, and you can tell me where, if anywhere, I go wrong for our listeners here, which is, so on the one hand, you have this corpus of text, and you do the distributional learning to learn what you can from that corpus of text. As we just discussed, that's not all there is, to learning the meaning of those words. So for example, as a human being, you learn by somebody saying ball, and they're holding a ball in front of you and you see it. And so you have all this other sensory data, and your observations about the world, which is in your brain, is forming this, more composite model of informational sources. And so in the study of linguistics, this idea is called grounding, which is, let's take the meaning that we have from distributional learning, but we still have to map that somehow to things in the real world or whatnot. And that's the process of grounding. Is that correct?
Yeah.
Okay.
Yeah.
And so when I was reading your thesis about grounding, I think one thing that really struck me about the way you presented it there, and something I'm not a big fan of, honestly, is it was presented as like very black and white, very binary. Like if I do some distributional learning, and that distributional learning comes up with, let's just say, whatever, a set of vectors, concepts, something another. And then when I want to ground them, I want to map that to, say, real world entities. It was presented in this way that every single distributional concept 100% has to map to something in the real world. And I don't get why. Like, why can't I have a partial mapping? Why can't I have 90% of my distributional concepts map to the real world, physical entities, whatever, and then 10% map purely to linguistic concepts themselves? Like, why does it have to be every single distributional feature has to map to a physical one?
I guess the question would then be what is in that 10%? If it's something like a syntactic property, it's just telling you about, how the word should combine with other words in terms of, word order or something like that, then I would say that's something you could learn from the distributional data, which isn't going to be grounded, right? That's not a semantic property if you have something like word order. But I think all of the semantics should somehow be grounded. Now, it might be in quite an indirect way. I'm not saying that everything in the semantics needs to be grounded, as in you can directly point to a real world feature and say, that is the exact feature, because obviously we've got abstract concepts. Right?
Yeah, exactly.
How do we ground
like this conversation, for example?
Right. I mean, we're communicating with each other, right? And we're not actually pointing to physical things and having this conversation.
Right.
And I think there are some big questions about what it means to ground an abstract concept. But I think that needs to be something which we have a more positive answer for, rather than just saying, oh, we have some distributional features which are not directly grounded. I think we should have some kind of explanation or some theory of how we can represent abstract concepts in a way that ultimately does connect to the real world. Because, we humans are entities in the real world. We somehow learn all of our concepts with the real world. How do we build up from, more concrete concepts and eventually get to more abstract concepts? I think that's a difficult question. I'm not saying I've got the answer to that, but I think that's something we should try to do and aim to do.
Yeah, I was just thinking that it seems quite related to the binding problem in AI. When we spoke to Jeff Hawkins, he said that because all of the cortical cells deal with complete objects, that was how it solved the binding problem, rather than having to figure out how all of these low-level primitives linked to abstract categories. But Walid on chat just said that you think it's more related to embodiment.
But I agree with Guy. I agree with Guy. Whenever we talk about grounding and embodiment, and it has to be connected to physical sensory input, we forget a huge part of our linguistic communication, which is abstract concepts. I mean, how do you embody or ground friendship or the notion of leadership? We know what a leader is, but do you sense it? Do you observe it? So that's a huge question that it has to do with emergence, probably what Guy was talking about, is how do we...
Yeah, I think it's connected to that, yeah.
Right. How do we, from the primitive physical concepts, how do abstract concepts emerge? Metaphorical mappings or whatever there is in language, we don't know. But
right, but I think what worried me in some parts of your thesis was that, for example, if a method, like let's say one traditional way of grounding was, or to try and link distributional learning with sensory learning, was I do my distributional learning, I get a set of, vector values, concepts, whatever, and then I do sensory learning, whether it's image recognition, who cares, and then I try to find correlations between those vectors, if you will.
Yeah.
And it said in there, well, we have no guarantee that every single one of our elements of the distributional vector will correlate with, with some sensory thing. And I don't think that should be a big concern, because, in point of fact, every single one of them will probably have a non-zero correlation. It may be epsilon, like it may have a correlation of 0.00001, but I think that that's okay. Like, it's okay to have partial grounding, because look, and you're kind of got some Bayesian concepts in your thesis too. And if you're a Bayesian, you don't worry about that, because down the road you may get some additional data which you can then add into your analysis, and you may get stronger correlations with that new data and those other things. So it's all provisional, it's all fractional, it's all partial. Like, why are we worried about methods if they don't give absolute, correlations for every single element with a particular data set?
Okay, so I think that there's two things I would say to that. One is that if we're just hoping that by having more data, then we're eventually going to be able to correlate it, that it's just a Bayesian problem. We haven't got enough data to infer those extra dimensions of meaning. I think that's very optimistic, that we will eventually be able to find that grounding.
Wow, I'm being accused of being an optimist, Tim. Did you hear that? Like, we need to mark this down to the listeners. I'm an optimist.
I think it's good that you're playing devil's advocate. I think it's a good question to ask. But the other thing I think is that saying that, we could be happy not to have everything being correlated, I think is in some sense giving up on trying to have a full theory of what it actually means to construct these abstract concepts.
Right.
And I think a full theory of semantics should be able to explain how abstract concepts connect to concrete concepts. And it's not like there's a clear distinction. There's going to be all kinds of things in between. So if we talk about, say, the example of friendship, right?
Mm-hmm.
You might be able to observe, people interacting with each other. But then you have to, think about actually, but not just the interaction as it is, but also what are the intentions behind that interaction? What's the person's theory of mind and so on. There's kind of a lot of steps you have to go through to go from observing two people interacting with each other to inferring something like, oh, there's some concept of friendship which is useful for understanding or somehow generalizing over the different kinds of human interactions that I observe.
Right.
And so that whole process of abstraction, I think, is going to be quite complicated, but it's something that I think we should try to be able to model.
Yep. Yeah. So let me just quickly wrap up there and say, fair enough. I agree with that. I think I just wouldn't want to abandon techniques just because they're necessarily partial while we're still working on a better theory, because we may close the door to very useful techniques. Was my worry there.
So I think in terms of is it a partial technique? So I cited also in my thesis, this contrast that Alexander Koller pointed out between bottom-up and top-down approaches in semantics, which is also came up in his co-authored paper with Emily Bender, the octopus paper. I think some people refer to it as the thought experiment they have in there, where if you have a bottom-up approach to modeling language, you say, okay, we have this model that can do something, and then we can add something to it. Hopefully get more and more and more of different phenomena covered by the model. And I think that's the kind of, the prototypical approach that you see in NLP is, okay, here's my model, now what can I add to it? But the opposite approach, or the top-down approach, is to say, what is language? What am I trying to model? Now, how can I get a theory that will get me to that end goal?
Right. What's the linguistic phenomenon I'm trying to explain? And which brings me to the question, I love where this is going, because when you said NLP, we mean NLP as it's done now, because it wasn't always the case. We used to study linguistic phenomena and try to explain them, not bottom up. But and some of us still do. But here's my question. I think the missing elephant in the room here is all of language learned, or is there some innate part that because it's related to bottom up and top down? Because if you look at the work of George Lakoff and his metaphorical mappings in language, how we built all this abstract space in language, which is all metaphorical maps from physical stuff, that whole thing is based on templates that I can't see that they are learned, no matter how much corpora you process. We're not going to learn that the contained in relationship is a transitive relationship. That's not learned. Do you see some innate part to language that it's just not learnable bottom up? There's some innate structure that we come equipped with. Like we have a visual system in our brain. We have a language module. That's Chomsky's hierarchy, that language is a biological organ. But without being a Chomskyan, I'm not a Chomskyan, but he equates language with vision. In other words, it's biological. We have a language module, which is not empty. We don't come in blank slate and we learn language from bottom up. Children don't learn everything.
I think this is I think this is ultimately an empirical question, right? How much is innate and how much is learned? And I think this is somewhere where machine learning approaches can say something interesting scientifically, because if we can say that actually for a very generic class of algorithms, something is learnable, then we don't need to postulate that it's innate, right? We can say, actually, this is just a general property which is learnable from the data. And so, for example, say with the famous poverty of the stimulus argument, as you mentioned Chomsky, this is something where actually at the time that, the poverty of the stimulus argument was first proposed, there weren't really good ways to quantify it.
Sorry, can you just introduce that for the audience?
So the poverty of the stimulus. So this is the argument that a human child in learning their native language or native languages, they don't have enough information in terms of what they actually hear or see, right? Their stimulus is too poor for them to actually learn a language and all the richness and detail that we observe.
In terms of positives and negatives.
Yeah. Right. So this is also the fact that, the children generally only observe positive examples.
Mm-hmm. I mean, sometimes they are corrected, but the idea
sometimes,
is...
but actually, But even actually, empirically, you find that children don't respond very well to negative feedback. If you tell a child, "Oh, you can't say it that way," it's actually not a very good way of teaching a child. Maybe even adults as well, But anyway, that's a different question. But empirically, if we can now test this, right, with large NLP models and train it on a human-like amount of data. So not the kinds of 1 trillion token corpora or something, but a human amount of data. So 10 million, 100 million tokens, that kind of size. And no more than that. If you have more than that, you're really going into something which is not realistic for human language acquisition. And you can see that actually there are lots of subtle syntactic effects which are learnable from that amount of data without having to postulate some very strict, innate syntactic mechanisms. I think it'd be interesting to see, how far can you push this? What's the scope of, possible phenomena which are learnable or not learnable with different, with different machine learning models. But I think this is somewhere where now we can approach that in an empirical way and actually quantify, what is possible with or without certain assumptions.
I think an interesting way to think about this, though, is from an approximation theory point of view. So I know Walid often talks about this Pac Learnability Theorem. So I don't think people are really arguing that any of this stuff is not learnable. It's more a function of how vast it is. So language is a countably infinite space of possibilities. It's huge. And neural networks are literally locality sensitive hashing tables, right? So there's just a complete disparity between the domain of language and the capacity of your model to learn it. Would you agree with that?
I feel like people actually often overstate the importance of language being infinite, because actually you get really complicated, interestingly complicated phenomena just looking at finite lengths of sentences. So I don't think you need to go to infinity to make these kinds of arguments.
I agree. It's not, the language we probably use is, there's a long tail of, the infinity is not something we ever probably come across.
Yeah.
But still it's combinatorially, you can, and this is not just on syntax. If you look at semantics, with 3 quantifiers in a sentence, you have 3 different scope orderings just to order the right quantifiers. The combinatorics are huge. Forget infinity. 6, 3 factorial, right? But going back to the poverty of the stimulus argument, although that wasn't the subject at all, but because you mentioned we're doing experiments now, which is great. Large language models are an experiment to verify whether Chomsky was right or not. Do children have not enough? Are they impoverished when it comes to enough stimulus? Well, large language models have told us already that because we're exceeding the number of things a child hears, actually an adult hears in a lifetime, and we can't resolve references. So obviously that's not how language is learned. Obviously is a strong word, but
right. So I would say when I said that there's experiments showing that certain phenomena are learnable, I feel like something like co-reference is a much harder problem because that does tap into world knowledge. In terms of actually, if you have to resolve a pronoun, what is it going to refer to? So I think the kinds of experiments where I think you can show a strong result in terms of what's learnable from a corpus is going to be more towards, for example, syntactic things where that is much closer to the form, but it's much closer to actually what you can directly observe in that kind of data. I think to get more general, to look at more general questions like resolving co-reference, I think you do need to bring in world knowledge. I think you do need to have some kind of grounded model if you actually want to model how humans do it.
Yeah, and I think, Wally, you and I sometimes get into this because what you've been talking about really is the context of the individual. So like, is an individual human being learning something versus is it already, given to them, encoded in them, whatever, that's one learning context. I also often look at the learning context of life in general, evolution in general, species in general, and therefore I consider, all the encoding that's in our DNA was learned by that larger process, right? Because in fact it did evolve. I mean, so I think sometimes this is where it gets a bit, confusing, but I think it's what Guy just said is almost obviously true, which is that text alone, and I know, Walid, you make this point all the time, text alone is not complete. And it isn't just the missing text problem, it's like the missing a whole bunch of stuff problem, right? Like, if somebody's holding a ball in front of me and moving it around in some complex way to pitch it, across home plate in baseball or something, there's almost virtually no hope that I'm going to ever be able to quantitatively explain that in any amount of text. Like it has to be almost visually observed.
When I say it's not all learned, look, the whatever is in our genetics is probably. The argument on the other side could be we're trying to simulate millions of years of evolution with learning, so we will get
billion,
there, right?
A billion, yeah,
right. But even with billions, there are things that, and I'm going to get to something that I discovered just yesterday that Guy wrote, which is of interest to me. The innateness that I talk about is stuff that we don't learn in the sense that they are given to us one shot. We don't have a choice to learn them because that's the way they are. So there's an interesting phenomenon in language, and I was pleased to see Guy wrote a paper about that with colleagues on adjective ordering restrictions. It's an amazing phenomena. I'll tell you why, because
can you give an example for the listeners? Because it is very interesting.
So it's very natural for us to say John bought a beautiful red car. We don't say John bought a red beautiful car, and the examples are infinite. I mean, it looks awkward if I say it the other way around. And this phenomena is called adjective ordering restrictions. And apparently it's universal. In other words, it's language agnostic and it's culture agnostic. It's just and that's what got me interested in it, because it told me that problem should shed some light on the inner language, the cognitive aspect of it. Now, it's amazing that, because it's universal, it can't be learned individually, or unless so there's some innate aspect to language that is universal. And when we say universal, right there, scientifically, we're saying it's not individually learned.
Well, no, I agree with you on that, but it was encoded by evolution into people. So, for example, if every single microchip I build interprets integers as big Indian, obviously, if I feed it little Indian data, like there's going to be a problem. But I think the point you're making though is that and what did you call it again? Adjective ordering restrictions, right? What's really curious about that is the cognitive kind of insights that gives you. So if you two could talk about that, it would be pretty cool.
So there's an interesting line of research at the moment, which is trying to explain adjective ordering preferences and other kinds of ordering phenomenon in terms of communicative efficiency. Now, I don't know whether this is going to go...
It's big Indian, little Indian.
Right, well, so it's a bit like that. So I don't know how far this line of research is going to go. Is it going to be able to explain all of the variation? But even if it explains some of the variation, I think that's interesting. If we can explain the fact that you would have a certain order because of wanting to put something earlier in the sentence, either because it's easier to produce or it's easier for the other person to understand, that could be one way that you can get this kind of phenomenon without it being, directly innate or even directly learned. It's something that even if you learned an unordered language, you might start to produce it in an ordered way. Another way you can try to explain this kind of phenomenon is in terms of not human evolution, but in terms of language evolution, in terms of how language gets passed on from generation to generation, and it changes a little bit with each generation. And you can try to model what's a more stable language. So it might be that the language ends up changing into a certain form, which is not necessarily a product of, our genes in terms of our innate learning, but it's a result of the combination of that with the way that we learn language, the way that we learn it and then pass it down to the next generation.
But what if now it's my turn to be a devil's advocate? What if there is an explanation, right, to this phenomena across languages that is so systematic, right, and it has to do with some formal mechanism? Then that would imply innateness, right?
Mm.
I mean, for example, I'll give you, and I'll send you a paper afterwards. It could be related to some strongly typed structure, ontological structure underneath, that says physical always dominates abstract, and so there's a type system that is consistent with how we do casting in even programming language. It's consistent with everything we know in mathematics. So suppose that explains it. That would be amazing, right? That language, there's a system underneath, which is a formal system that subconsciously we follow. We have no choice. That's my interest in this problem, because
I think it would be very interesting if we can shed light on how human cognition works in terms of, because it could be that, all of these things are relevant, that we have, some of the ordering preferences come from some deep cognitive some deep cognitive setup in terms of how we naturally, innately conceptualize the world. Some of it could come from how language gets passed down generation to generation. Some of it could come from trying to be efficient in our communication. And all of these things are going to play a role. And I think it's going to be an empirical question of trying to work out, where do we draw the line? How can we quantify the contributions of these different factors?
Yeah, but it is an interesting line of work, and because I know probably Tim and I may be fans of a lot of the free energy, type arguments that life is conducting this optimization, and so things like efficiency and error correction, transfer, all of that matters, right? And so kind of this ordering, and it does get down to, and I kind of picked the example randomly, but I'm realizing it's more relevant, as we're continuing to talk. The big Indian versus little Indian and CPU architecture has real world implications, right? In terms of, error correction and specificity, efficiency, transfer, et cetera. So,
I mean, error correction is actually something which people have applied to explain, for example, word order preferences or case marking, things like that, where if you hear someone under noise, then ideally you want the language still to be, the message still to be understandable, even if you have some amount of noise. So robustness to noise is one argument that you might prefer a language to have some structure over another structure.
Right.
Isn't it remarkable? We're talking about linguistics now, but there are analogies to cognitive science, and we find, even though we're talking to a variety of different people, we're always running into the same ideas, like logic, for example, and epistemology. And Keith was saying before the show, apparently there are foundationalists who talk about axiomatic knowledge, and there's coherentists who think that it's all about the connections and the structure, and there are ideas about epiphenomena or strong emergence or reduction.
I definitely think that you do get these interesting connections between, cognitive science, machine learning, linguistics. And I think that's, why I'm so interested in the field. It's because you have these connections between so many different areas.
Well, I mean, do you agree with Chomsky that language is a system of thought, for example?
People are always afraid to give an opinion of Chomsky either way.
Yeah, I feel like Chomsky is
right?
Chomsky has a
I've
very,
been avoiding
very,
coming off mute to respond to these.
Yeah. Chomsky has a very complicated legacy, I think.
Right.
And
he changed his mind a few times, actually. But
yeah.
Don't get me in
more
trouble,
difficult
Wally. Come on.
I would say that language is definitely deeply connected to thought, but it's not the same as thought. And there's actually some interesting experiments where you can do things like, for example, when people have tried to test the Sapir-Whorf hypothesis, so the idea that language influences thought. And this is one of these controversial ideas, because if you state it very strongly, it's obviously false. And if you state it very weakly, then it's obviously true.
Right.
So I think the interesting thing is, can we state it in a way which is not trivial,
Yeah.
but still says something interesting, right?
Right.
Yeah.
And there are these interesting experiments where you can get people to try to do some task, and you can try to distract them in some way. And you can find that if you distract, their linguistic system, so they're having to do another task at the same time that's linguistic, then that inhibits a Sapir-Whorf effect. While if you don't do that, then you do see an effect. So you get these very, subtle, conflicting, yeah. And so from this kind of experiment, you can see that the way that language connects to general cognitive behavior is actually quite complicated, because it's deeply tied to some aspects of cognition, but it's not that all aspects of cognition are linguistic.
This is what I was going to say. I mean, we obviously think about things that are not linguistic in nature. I mean, when I'm playing chess, I'm thinking, but I'm not sure I'm thinking in language. But you do agree that language was the medium of transmitting thoughts. I mean, so it's a subset. It's not, we think about many other things. Not all thought is linguistic, I agree. But linguistic utterances that we externally transmit come from thoughts. They are an expression of a thought. No, I mean, that's Jerry Fodor's language of thought, kind of, which is related to Chomsky, but it's even stronger. In other words, language is just an artifact. Yeah. It's a coding scheme to encode externally my thoughts. Right. That's it.
That's another person with a complicated legacy, I would say.
Yeah. and actually, I'm afraid of criticizing Fodor more than Chomsky. He can be.
Can we move on to the topic of vagueness? Is that okay? I think.
On this topic, I'm very happy to talk about.
So actually, you have some interesting takes on it. So maybe just give us a 1-minute synopsis.
So vagueness, as it's usually defined, is the problem that you don't have clear boundaries for what words denote. So, for example, something like red. The word red doesn't have a clear cutoff between red and orange or between red and purple. There's some kind of area in between where it can be uncertain whether a particular color is red. So that's an example of vagueness. And so there's previous work, so not my own work, that has analyzed vagueness in terms of a probabilistic approach to meaning. So saying that actually, rather than having a clear true-false value for every sentence, we could have a probability of a sentence being true. So if I say this is red, there could be some probability that's true. So more recently, I've been working on vagueness and thinking about it from a more machine learning point of view. And I think actually, if you start to think about learning with real data, and in particular learning with high dimensional data, because high dimensions are really unintuitive. And I think this is somewhere where actually a machine learning approach does say something new and interesting compared to classical discussion of vagueness. If you have a really high dimensional space and you're trying to learn a concept like, what is red? Now, even for colors, maybe you can describe that in a 3-dimensional space, but even in a 3-dimensional space, it's interesting, right? You can say, what's the region of this 3-dimensional color space, which is red? You could, observe a few points, but if you want to generalize, say, okay, and now I've got a new color that I've observed, is this thing red? The higher the dimensionality of the space, the more difficult it is to actually be certain about your generalization, to say, actually, is this thing an instance of some concept I've learned before? And the real world is high dimensional. I don't think we can really argue against that. So actually, when we have to learn concepts in a high dimensional space, we're bound to get vagueness, because there's just no way that we could observe enough data to really nail down a precise concept.
Yeah, it's very similar to the grain of sand. That if you keep piling up grains of sand,
with the heap.
At what point does it become a heap, or when do you become bored if you keep plucking hairs?
Well, that's an interesting example, right? Because so let's just take the heap example. It's often presented in this way that we can describe a heap in this one-dimensional way, right? A heap is a number of grains of sand. So is 1 grain of sand a heap? Okay, no. It's 1,000 grains of sand a heap? Okay, that seems like it could be a heap. But actually, if you think about it, a heap isn't a one-dimensional object. If you think about, actually, we've got these grains of sand, let's even assume that they're all the same, shape and size, but how we configure them in a space is going to change whether we call it a heap. If you laid them flat on a table, That's not a heap. Even if it's 1,000,000 grains of sand, if you lay them flat, that's not a heap. Right? That's a flat.
Right. I mean,
maybe the beat.
I like the analogy, but let's take something like tall. I mean,
Yeah.
tall is roughly a one-dimensional concept. I mean, we're talking about
even for
we're
tall.
talking
So
about height, one dimension.
right.
So
Okay, height. But what's the height of a building? If you have an antenna on a building, is that
that okay?
part of the height of the building?
Now we're moving from vagueness to ambiguity. A big elephant is not a big ant. No, that's vagueness. I thought is the vagueness of a predicate on a specific object.
But I think height itself is a concept, and I think height. If you try to define height, you have to learn what is height. Actually, height is not something that's given to us in the real world. It's not a direct. We can't directly experience height. We have to learn what height is. If I ask you how tall is a person, it's not just what's their, vertical dimension. If they're lying down, that doesn't make them say, oh, suddenly John is very short now because he's lying down, right? That's a ridiculous thing to say. So we have to learn a concept of height that means something in terms of what's the height of a person, what's the height of a building, actually is a learned concept. So even height, I think, is not a one-dimensional concept. I think that still requires some amount of generalization, abstraction.
To what extent are these epiphenomena, like red, or let's use the concept of running. So that is an epiphenomena, and it's something which I don't know whether it emerges from our society or it emerges from somewhere. And now it's got this weird thing. It's a bit like the blockchain. It seems immutable. I mean, you couldn't change what running means, but it's not a Platonic thing, is it? Because running, it means many, many different things. So it seems to be something that it's not given to us by the universe. It's something which has emerged in humanity. But would you consider that a form of vagueness, or is that different because it can be more distinctly described? You could argue that the Platonic ideal of a circle, for example, is very clearly, from a precision and recall point of view, it's very clearly definable what I mean by a circle. But are you talking about vagueness in the sense that it's genuinely difficult to...
concepts in a minute. So with something like running, okay, now we have I think as a related issue of polysemy, which is, I think we have different kinds of senses of running. Right. I think that's a related problem. It's not quite the same thing, because you could have a word, I mean, theoretically, like hypothetically, you could have a word that's polysemous between a number of senses, and then you could ask whether each of those senses is vague. I think they end up being connected, because if you actually try to decide what counts as a sense of a word,
right,
then you have a question of how do you delineate the different senses of a word, and they might start to run into each other. So I think they are connected in the sense that they're both dealing with a question of how to generalize.
Or what's the borderline, or what's the demarcation point? That's what's common between them, right?
So, but for polysemy, we have what's the demarcation between different
shades,
there's different clusters of usages of a word. So if you have there's a certain cluster of usages of the word running in terms of physically going out and running on your two legs, right? Animals running on other numbers of legs. And you've got running errands, a machine is running. We have these different clusters of usages, and we could, think about how do we actually generalize from each of these, these clusters, or even just single examples.
There's a discrete versus continuous thing as well, because with red, it feels very continuous. Whereas with an abstract category like sour grapes, for example, it might be possible to define another discrete situation that could get attached to that abstract category.
Why would an abstract situation be more discrete?
Well, so in the case of running, because of the polysemy, there are many completely disjoint situations which can have the same meaning.
But I wouldn't call them completely disjoint.
Okay, why not?
So I think you do. So if you actually try to, sit down and write, what's the list of possible senses for a word? And if you look at, what lexicographers do, so people who write dictionaries, there's a famous quote by the lexicographer Sue Atkins, who said, "I don't believe in word senses." And, this is someone who writes dictionaries, writes word senses, right? So she writes word senses, but she doesn't approach it as thinking, oh, there is some list of senses that exists, I just need to find it.
Right.
It's more, what's a useful way of describing the uses that we have? And there's going to be some borderline cases of, is this a separate sense? Is it a combination of senses? Do we have to make a new sense? Is it a existing sense? There's going to be these borderline cases. But if you're writing a dictionary for someone to read, you've got to decide what's actually useful to tell someone, here are some different groups of usages of this word, which is something that, because ultimately humans got to read the dictionary, we're not writing it.
So what you're saying is when we're defining how polysemous a given word is, it's an ad hoc decision. We say at some point, you know what, this shade of meaning, there's no need for it. It's almost like the previous one. That's enough. So people that did WordNet, actually, they had to make these ad hoc decisions. Like, these are enough. 7 meanings are enough for line. We're done. That's it. We're trying to be too picky by having another shade of meaning. So I agree with that, but there's still a difference between how many meanings running has, whether it's polysemous or metaphorical meaning, like the machine is running, and the fact that one sense, not different senses, one sense itself is vague. I think that's what Tim was probably like.
Well, the thing is, I worry for the symbolists because this vagueness problem is very difficult to overcome, right? The ambiguity, not so much, right? Because I was going to talk about this there. Isn't it remarkable that human communication is not plagued by ambiguity? Walid points out in many of his writings that human communication is characterized by the so-called missing information problem, which is that you don't say everything that you mean. So ambiguity allows humans to increase the transmission efficiency of their language by relying on colloquial knowledge and extrapolative local processing on the receiving end. You said in your book chapter with Bender that a well-constructed grammar should be expected to return multiple parsers for an ambiguous sentence, but it's completely different to vagueness. I mean, that's something which could be resolved because presumably there was one human thought behind an utterance when you say something.
Well, first I want to object to something, which is I don't know why. I mean, maybe it is, but vagueness shouldn't be hard for symbolists to deal with any more than curvature is hard. Well, because curvature isn't hard for a mathematician to deal with, right? Like in a lot of ways, straightness versus curvature is kind of like precision versus vagueness.
Tim, here's a solution for vagueness that was developed by symbolists like Jerry Hobbs. So, for example, if I say tall, it is a vague concept. Who's tall and who's short, and at what point is 6'5" tall? Okay, and here's one solution that Jerry Hobbs. There's something called typical element, typical instance, right? So someone is tall if their height, because every vague concept has a dimension, many dimensions sometimes, like Guy said. Let's stick with one dimension for now, Guy, for tall. So let's say tall is a one-dimensional vagueness kind of problem, height. So someone is tall if their height is greater than or equal to the average height of a typical element. So there are ways to deal with it, and it does a good job. I mean, someone is, you know what I mean? Someone is bright if they are smarter than the average IQ person. So we say, so there's a typicality, there's a typical, they call it in cognitive science, prototypical concepts. There's a prototype, right? And if you're tall, if your height is higher or equal. So there are ways to deal with it. I don't know if
so if I could add two things to that. So on the topic of prototypes, I think that's one way that you could define was kind of in a funny way, a prototypical one sense concept.
Right.
Would be a prototypical concept just has, a core idea, which is the best example of that. And then if you're closer to it, it's a better example of that.
Right.
A polysemous concept doesn't have a single prototype.
Right. That's the difference. Right.
And so you can have a polysemous concept, which you have to describe in some way that's more complicated than having a prototype. Now, whether that's a small finite number of prototypes, or whether it's something that's altogether, more fuzzy than that, I think that's an interesting question.
Yeah,
but that's one way we could think about, what does it mean for something to be polysemous?
Yeah, I mean, from my perspective, and I only maybe a couple months ago was I told I really needed to research vagueness more, because up until that point, and I think still now, from my perspective, the epistemic kind of viewpoint, which is just to embrace probability, kind of resolves all these problems. Like I still haven't seen yet any good or any convincing for me objection to just understanding that almost all knowledge and, categories, et cetera, are probabilistic. I mean, sure, there are exceptions to that rule, and that's fine. We have certain mathematical concepts that are quite, precise and well defined. But it seems to me in your thesis, you've kind of wholesale embraced this probabilistic, viewpoint as well, not only for vagueness but other, useful things. And what I thought was really interesting was this argument about the dimensionality. And we just produced a pretty interesting Street Talk episode that went in, great depth about the curse of dimensionality and these inevitable problems that you're going to run into in high dimensional use cases where there's just no way in hell. Like you're going to have a non-vague, boundary somewhere. And so am I correct that you're embracing probability as a solution to this, and you're not aware of any real difficulties, or are there still remaining philosophical objections and difficulties that you believe are not surmounted?
So I would definitely agree that I fully embrace the probabilistic approach. I'm not aware of any serious objections that still remain at that point. I mean, maybe Walid has got something to raise. So on the example that he gave of, for example, describing tall in terms of having, some reference point that if you're taller than some, the average height, say, then that counts as tall. There is a way to express this in a probabilistic way in terms of Bayesian inference in communication. So if we say that, okay, tall means taller than some particular reference height, but that height is not fixed, so we have some kind of distribution for that threshold. Right. And then the listener then has to infer, well, given what they know about the world and what the speaker might be trying to say, can they infer what the meaning is?
Right.
Based on just directly observing that.
Actually, that's why tall in the Middle East is different from tall in Holland or in Norway. Right. So because you're doing, because the
different
solution
prior knowledge
suggested, right? You have a distribution and you're calculating that real time. So it's the two are related. There's a distribution. There's a population that you're. Yeah. What does it mean to say a typical element? Well, you're saying, this is my data. This is my distribution. That's what a typical element is, right?
So, what's interesting too is that you bring up this, okay, the threshold may have a distribution, right? A probabilistic distribution. And I believe this is original to E.T. Jaynes, and who is a big Bayesian and obviously communicator of Bayesian kind of point of view. And he brought up, or he created rather, this idea of what's called an AP distribution, which is that a probability itself can also be probabilistic. So you can have a probabilistic distribution of a probability. And he gives this great example of, consider, for example, if somebody's flipping a coin, okay, and you're asking yourself, what's the probability that it's going to come up heads, okay, and you flip it, 5 times, and it comes up heads 5 times in a row, you still really wouldn't change your distribution that much. You would still guess that you just got unlucky, and the coin is probably still fair, just based on all the strong evidence you have that coins usually come up half heads, half tails. On the other hand, consider the proposition that there's life on Mars, okay? If we come back and we launch a satellite or a probe up there and it lands and it finds something that is pretty much unambiguously, bacteria, you're immediately going to decide, okay, there's life on Mars. Even though both propositions in the beginning were kind of 50-50, you might be 50-50 on whether there's life on Mars, 50-50 as to whether it comes up heads. You're much more certain about the heads than you are about Mars. And as soon as you get some new data, you'll radically change your view on Mars. So I think when you fully embrace kind of probability and this Bayesian perspective, a lot of things in the world make much more sense. And you stop worrying about like, is tall 6 feet or 6 feet 4 inches? Like, I don't know. I mean, you get this new mathematics that lets you handle all this in a uniform way.
Yeah, I think that example shows the importance of hierarchical probabilistic modeling. So it's not just we have, one random variable that we are observing, like say whether the coin comes up heads or tails, but there's a a hierarchy of random variables. So is the coin fair in the first place? And then based on that, that value, we can then decide what's the probability of a particular throw coming up heads or tails.
This is interesting because I think there's a qualitative aspect to this, not a quantitative aspect. I mean, the example of Mars, the indication I have is qualitatively different. It's not a quantitative issue. So I don't know if it's just a question of probabilities all the way down.
Well, the AP distribution gives you a way of quantifying that qualitative like concept, which was, it gives you a mathematics that captures that difference. The person who starts off at the beginning and says, I'm 50-50 on Mars and 50-50 on heads, but I have very different beliefs in those two things. This can capture that.
Okay, so we're back to the belief, right? But I don't know how that is related to vagueness.
Well, vagueness would be that if I have a category or two categories, whatever, that whether or not an object is that category is a probability. It's not a 0 or 1 assessment. It's that there's a 50% chance that I'm tall, and so as Guy brought up, if somebody had a certain prior context and they were evaluating, right. Oh, he said that John is tall. I wonder how tall he is. They would have a probability distribution on that.
I think I don't know if we're missing something here. Nobody doubts that there are vague, uncertain, imprecise concepts. Nobody ever doubts. Anybody does. Even symbolists don't doubt that. I mean, right. Tall is a vague concept. Nobody doubts that. The issue is, do we have to defuzzify at some point? So I'll give you an example. And they studied this. Fuzzy logic is unsound at some point at the highest level. If I say, John likes every famous actress, Liz is a famous actress, right? At that point, John loves Liz by deduction, regardless of how famous she is. At that point, I have to say she's famous. It becomes a binary decision. Otherwise, you can't make inferences. So the point is not about, nobody doubts vagueness or uncertainty. The point is you need a higher level of reasoning where you have to collapse the fuzziness at some point. There's a fork.
I disagree. So a Bayesian would just continue working with probability distributions from start to finish. They would never, ever put in a threshold or discretize until it reaches a decision point. So as soon as,
right.
Okay, but decision theory is kind of a whole separate, category, right? That's I've got my knowledge, which is represented by probabilities. Now I need to decide an action, and I can only take one action or whatever.
Okay, so here's this does come to an interesting point in terms of how can we formalize a probabilistic logic.
Right.
Because actually there are different ways
that it's already done, and it's probability theory.
There's different...
There are different approaches.
The difficult thing is not just when we have a small number of variables, but when we want to have probabilities for logical propositions, there are different ways that you can bring in the probabilities. And depending on how you do it, it might look more or less paradoxical in terms of making inferences like the example that Walid just gave of, but if John loves every famous actress, Liz is a famous actress. Right? If we want to do that inference, how do we set up the probabilistic logic so that we can actually get an answer out for that question?
Right. That's the trick. I mean, obviously, you can deduce that John must love Liz. How do you make the calculus work so that you can make that inference? Right.
And what's interesting is actually that, so one benefit of fuzzy logic compared to a probabilistic logic is that doing inferences is really easy. You just do it on a truth functional level. So for example, logical and, logical or, we just have a fuzzy logic version of that. It's very easy to push it through. With probabilities, it actually gets very tricky because if you start thinking about the joint distribution of all the different logical propositions you could have, this just becomes completely intractable very, very quickly.
Right. Belief networks try to do that, but yeah.
Well, the only problem with probabilistic graphical models is you have to design the bloody things.
Right. Exactly. So this is an interesting thing that I found in my work is that if you do want to set up a probabilistic logic and you want to scale it up so that you can deal with, sentences that humans actually use in practice, you start to get completely intractable models.
No, I do want to just slightly object to something, which is So first of all, there is only one mathematically sound generalization of logic, and that is probability theory. Now, as you point out, like it does create these intractable problems, and so all these other fuzzy logics are hacks. Okay, they're hacks on the one true sound probability theory to try to come up with things that are more tractable, but that's why they run into these consistency problems, paradoxes, yada yada. So I do want to just set that goalpost, which is, look, we have the one true mathematical solution to this, and all probability theories are isomorphic, to the one that we're familiar with, which is conditional probability theory with the sum and product rule and probabilities
right, so I agree with,
bounded to 0 and 1.
I agree with that part. But the question is still, so just to make it more concrete, if we define a logical language, so we have all the logical symbols we want to use in the language, the syntactic rules for combining them. So we have our set of logical propositions. And for each logical proposition, we have a true or false value. And so now we have to define a joint distribution over all combinations of truth values. And so that's the goal. And the question is, can we do that in a feasible way?
Well, so look, so there is the one true way to do it, which is the sum and product rule.
This is.
So, but I did just want to make it clear for the listeners, which is now we're talking about how can we actually engineer something that we can do in practice. And I'm 100% on board with you, which is it's an intractable problem. It's very difficult. People come up with, different solutions to it. But I just want to quell the idea that we don't have a consistent mathematical framework.
Yeah.
That's not true. We don't have a consistent set of hacked rules that we can actually compute.
Right. I mean, for me, look, nobody is questioning that probability theory is a sound mathematical framework. Okay, because it agrees with logic. It's a generalization. It agrees with set theory and all of that. I mean, and is an intersection. All these things are consistent. The probability theory is a valid science. Nobody's doubting. The issue is not this. The issue is, can we use it to model human type reasoning without getting into funny stuff? Because people have worked on that. Right.
You're not going to get into funny stuff, but you may get into things you can't compute. So if you want to say, can we use it to tractably model, then I would say, okay, I get you. That's difficult and open question.
But this is somewhere where I think there are interesting things that we get if we try to think about the tractability. Because if we look at, for example, quantified expressions like, every mammal has 4 legs, or whatever you want to say. That one's not true if you say humans have 2 legs. If you have every X is a Y or some X is a Y, trying to do this quantification, if we have a probabilistic logic, it becomes very, very expensive.
Right.
Especially if not only do you have to do this quantification, but if every single X and Y you have to consider has a vague concept behind it. So you've got a probability of everything being an X and a probability of everything being a Y. How do we actually do this quantification? It becomes very, very expensive.
Understood.
Yeah. So if you then take generic sentences, so not every X is a Y, but something like birds fly, or ducks lay eggs, where there's no overt quantifier. Now, these kinds of sentences have this what seems like a weird paradox in that you have, on the one hand, they seem much harder to define in a formal logic. Like if you say every duck lays eggs, we can say, we can exactly know how to compute whether that's true or false. If you just say ducks lay eggs, now does that mean every duck lays eggs, or some ducks lay eggs, or most ducks lay eggs? And actually, if you think about it, you realize, well, hang on, actually male ducks don't lay eggs. And, baby ducklings don't lay eggs. So actually, it's a minority of ducks that lay eggs. And yet somehow it's completely natural to say ducks lay eggs. And so somehow we have this weird, what seems like a paradox between, on the one hand, it's harder to define what it means precisely. And on the other, they're much more natural in terms of children pick up generic sentences much earlier than explicit quantifiers. Adults process generics much faster than explicit quantifiers. But this makes sense if you have a probabilistic logic where they're actually computationally simpler to calculate. where you don't have to do this very expensive calculation marginalizing out a huge number of random variables. And actually, you can have a much simpler calculation for a generic sentence. And so this is where it does matter how you set up the logic, because we're going away from a classical logic. We're saying that actually this doesn't correspond to a classical quantifier like for all or there exists.
Right. Yeah, and that's probably why, it was probably similar efficiency considerations that caused the brain to develop in such a way that it has all these cognitive biases and kind of errors of reasoning that happen, perhaps.
Yeah, although the question is whether when you go all the way down to the base layer that there is actually a solid semantic foundation or whether that fuzziness remains. On the subject of this, I wanted to talk a little bit about grammar engineering because we've been talking a lot about vectors and distributional semantics and stuff like that. And I know I'm talking to a linguist here, and you're interested in much richer data structures. So a couple of questions about your long tail of large-scale grammars, which you spoke about in your recent book chapter with Professor Emily Bender last year. It was called Computational Linguistics and Grammar Engineering. So you illustrated the landscape of computational work in head-driven phrase structure grammars, which is a bit of a mouthful. So these are generative grammars. They're used as indeed they're used as rich data structures to represent syntactic language. They have a rich type hierarchy, which you thought would make them very robust over time. And you said in the book chapter that you appreciated the clear separation of the formalism from the overarching linguistic theory and the ability for the formalism to model what we're going to call long-tail peripheral phenomena as well as core phenomena. So most implemented grammars are built with the goal of handling naturally occurring text, which means they'll be able to handle a wide variety of linguistic phenomena that are not always treated in the theoretical syntactic work. So can you give us a little bit of background?
Well, and specifically, if you wouldn't mind, so I'm familiar with, the context-free grammar, whatever that you might learn like in a CS course. Can you just explain what exactly the relationship to that in a head-driven phrase structure grammar is?
Yeah, so head-driven phrase structure grammar uses a typed feature structure formalism. And so as Tim just mentioned, the formalism itself is Turing complete. So you could in principle write a grammar which could calculate, any computable language.
Okay, so it's a larger class than CFGs and
yes, definitely.
And so is it context sensitive as well, or?
No, it's Turing complete. In the full formalism is Turing complete. Yeah. But in practice, you're not going to use the full Turing completeness. I mean, I think it would be a bad idea to try to use the full Turing completeness. So this is that distinction between what's in the formalism and what is actually in a particular grammar.
Right.
If you're trying to, model a particular language. So the way that the formalism is defined, rather than having, so say if you're familiar with the CFG, you have atomic categories. So if you have each node in the tree, it's just a single category.
And that's a context-free grammar.
Mm-hmm. That's a kind of context-free grammar. Yeah. If instead of having a single atomic category as you have in a context-free grammar, if you have a structured object, so you have a number of features, and each of those features has a value, and the value is itself it could be another structure with its own features and its own values. So what you actually have is it's a directed acyclic graph where each node has some type and each edge has a feature. And so you have this richer structure to represent each node in that phrase structure tree. So that's it's head-driven phrase structure grammar. So we're still using this phrase structure. So we can have a tree, but then each node is not just a single atomic object, but it is this feature structure.
Right. So each node isn't a token. It's a more complex structure.
Yeah,
right?
Exactly.
Okay.
Yeah. And by using this more complex structure, this is useful even if you don't have to go to the full Turing completeness to see the usefulness of this. It's useful, for example, if you want to decompose something. For example, if you want to look at a verb in terms of it's got a tense and it has to agree with the subject in terms of its person and number. The verb might have a certain number of objects. So you have all this kind of structure, which you can then specify in a more independent way, rather than just saying, oh, well, we have one one non-terminal node, which just has a specific category which has to encode all the information. We can break it up into these smaller parts. And so even if you have even if you wanted to describe a context-free language, you could do it using this more, this richer formalism, so that you can have a much simpler grammar to describe exactly the same language, even though it's a context-free grammar.
Interesting.
You can describe it in a much more efficient way. And so from a linguistic point of view, you can state generalizations more easily.
So for example, if anyone's ever looked at the grammars for programming languages, they sort of have to introduce all these kind of hacked intermediate, tokens, which can then expand into something that would kind of be collapsed into a more efficient way to represent kind of branching alternatives rather than kind of hacking all these intermediate nodes. Is it something like that?
Yeah, something like that. Yeah.
Okay, but I mean, one of the things here is we want to have a rich and structured way to represent semantic meaning in language, and you talk about this really interesting long tail phenomenon of linguistic phenomena, I suppose. So it's very similar in neural networks. We also have this long tail, and most of the capacity in a neural network is wasted learning the low frequency attributes, which are the things that hardly ever come up because they're just really weird. But you said that when working with actual data in large scale grammars, it quickly becomes apparent just how long this long tail of peripheral phenomena.
Yeah.
So you gave this really interesting example just to bring it to life. You said, it is incumbent on you to speak plainly. And you said it was an example of a low frequency type, which requires an expletive it subject, an obligatory up-on prepositional phrase complement, an infinitival verb phrase complement, which establishes a control relation between the object of on and the verb phrase's missing subject. So that's just one example of this linguistic template. I mean, how many are there? How can we reason about this?
I mean, these are really, there's a lot of these templates. So I have to say that this isn't an example that I came up with myself. So this was from the English resource grammar, which has been developed over many years now. The person who's had the most, the main architect of the grammar is Dan Flickinger. And so Emily Bender's worked with him for many years. I was the junior author on this paper with Emily. But that example sort of shows the vast diversity in what's called argument structure. So how a verb can combine with its different arguments. And so you might, in an introductory course, learn that, okay, a verb could be intransitive or transitive or ditransitive. And you have a few examples of these. So then you could write, a context-free grammar that has these different verbal types. And this would cover a lot of examples. You can get a long way with a relatively small number of different what are called subcategorization frames. So that how a verb can combine with its different arguments. But actually, when you look at a big corpus, and linguists are often interested in that long tail, they're not happy to just get, we've covered 95% of the sentences. Actually, we want to cover it as much as we can. And if you look at this long tail and you find examples like it is incumbent upon you to speak plainly, that actually this has a very specific requirement in terms of what it combines with. And so if you want to write a large-scale grammar, and so the English resource grammar is a very large-scale grammar, there are, I don't know exactly how many types there are, but it's a huge number of types in the grammar to be able to cover all these different types of verb that you observe in practice.
Okay, that's fascinating because what I love about this as a computer scientist is the deep learning approach is very much a black box, and this is a very principled way of going about doing it. But you do say, though, that you can still apply probabilistic approaches almost as a second pass. So there are many ambiguous pass trees that might come from such a grammar, and then you can start to apply some supervised learning and so on that second stage. So do you think that is the way forward?
I think that's part of the way forward. I think, in the long term, it would be great if we had a way to induce this kind of grammar rather than having to sit down and, write all the rules by hand. The reason that, that this has been done is because it's really difficult to induce the rules in a way that's precise enough that actually it does it what we want it to. There is work on trying to induce grammars in a more principled way. So not just a large language model, but in a way that actually we can say very precisely what's the kind of structure we have in a way that you have very, very clear generalizations, very clear predictions about what is grammatical or ungrammatical. And you might argue, okay, maybe there are some cases where we don't want to have a exactly binary prediction, but still to have a model where we can have this very clear structure, I think in the long run it would be great to, and there's ongoing work on trying to induce this kind of thing. So, for example, taking the grammar as a starting point, we could say, well, can we have a model that can produce these structures without having to use exactly the typed feature structures that I mentioned before? Do we have to use exactly that structure in order to derive the semantic structures that the grammar produces, or can we derive them in a different way? So there's work, for example, on using hyperridge replacement grammars, which is a fancy kind of expanded version of trying to use graphs instead of having rather than working with trees, we can work with graphs. And I'm trying to use other approaches that might be able to derive the same kinds of relations that the grammar produces.
Fascinating. Yeah, because I'm just reading some notes you actually quoted. There was a paper in 2002 by Tortanova that said on the ambiguity thing, roughly half of the ambiguity in the Redwoods tree bank was lexical and the other half was syntactic. And apparently they were showing that combining the semantic and syntactic information was useful for reducing the ambiguity. But I'm just trying to get my head around just how much of a big problem this is, because there's the ambiguity problem. We were talking earlier about the possibly the combinatorial. I don't know whether you'd prefer to use the word combinatorial or infinite blow up of language. But as I say, there's a lot of structure to it. There's a long tail. There's so much structure to it. So there must be a route out of this.
Yeah, and I think that's somewhere where we kind of have to rely on computational techniques because it is combinatorial. It's just really difficult to do this kind of work with pen and paper. You just miss so much of the possible predictions that the model would make. But I think it's also interesting, when you bring in this, when you bring in a machine learning perspective, because if you think about the structure in terms of how can we generalize. Right, because this is always generalizing to new sentences. So if we have a training data of sentences we've seen and we've got some parsers for them, we want to generalize to a new sentence. So we have that machine learning problem. And so I think we do have this interesting connection between the learning problem and the structure that we want to learn.
And final question. So there are loads of folks on LinkedIn now that are saying they are NLP experts, and they're using models which they probably don't understand, and they're trained to do a specific task very well. What's your view on that? Do you think that it's something that we should be concerned about?
I mean, I'm not on LinkedIn myself, so I don't have first-hand experience of what people are saying. I mean, there's definitely a huge growth in the field. I think there is a potential danger in terms of whether people understand in terms of applying it in practice, whether people understand, what are the strengths and weaknesses of these models. Because there's definitely huge improvements that can be made, with these, say, large language models. we haven't talked about them that much in this. I mean, little bit we've talked about them, but not that much in this conversation. Because, I've been talking more about, how to model human language use, human language acquisition. If we're trying to think about practical tasks where we don't actually necessarily need to worry about, how humans do something with language, but we want to just build a system that can do something, then I think we need to be really careful about questions which are not necessarily technical questions, like how do we apply the Hugging Face library, or, how do you train the model, but actually questions about methodology. Are you certain about what the model is actually capable of? Error analysis, questions of what's the transparency of the model, fairness, what are the kinds of predictions the model is going to make, and how is that going to have a real world impact? I think it's good that there's more discussion in the community now about questions like transparency and fairness. But those are questions which are, they're not purely technical questions. I think Kate Crawford put it very well, but she said that bias is a social issue first and a technical issue second. And I think the danger is if people are too confident in what they know and aren't aware of the bigger picture. You know, in terms of the machine learning aspect, if you know how to apply the Hugging Face library and train a system that can, you know, get a high score on whatever task you're doing, that's a little piece in a much bigger picture of, well, where did the data come from? What are the, you know, do you really understand your data? What's the system actually going to be used for after that? What's the impact of that? What's the ways that it could go wrong? Because, you know, every system is going to go wrong at some point. And these aren't purely technical questions. So I think we do need to be, you know, humble enough to recognize when we do need to, you know, talk to people outside of NLP and actually understand what's the wider context of that.
As you alluded to, these are very difficult questions. And in fact, there's a lot of vagueness, you know, built in them as well. You know, I mean, like what is bias can even be a vague or very difficult to pin down and define, you know, concept.
Oh, it's very difficult.
Right. So, I mean,
which is why I think, you know, we need to be careful when, if someone, you know, self-proclaims to be an NLP expert and then says that they, you know exactly what the model does and, it's not biased because, you know, I didn't program it to be biased, or say something stupid like that. Where actually there's a much bigger picture there that you need to be aware of.
Yeah.
I mean, this is now just, you know, straying outside of my own research because, you know, my core research is much more on the linguistic side rather than the applied side. But, I think as a field, we need to be aware of the bigger picture.
Well, I think, to be honest with you, I take a little bit of a different take, which is that I think these questions are so difficult and complex. They're really a field of study and a science like on their own. And I'm doubtful that a person who may legitimately be an expert in NLP, I'm doubtful that they actually, that a typical human being has time to develop the expertise necessary to evaluate their work in that broader context. Like, I think what's going to happen in the future is we're going to go, like, for example, I don't do my own legal advice. I go to an attorney when I need legal advice, right? And I probably shouldn't even be doing my own tax accounting. I should probably have an accountant doing that, although TurboTax, you know, helps a lot. I think what we're going to have is a profession and tool sets that make it easier for people to evaluate the impact of their work or potential, you know, pitfalls, and maybe say, hey, like, you know, university, can you please submit this experimental design for, you know, whatever we want to call it, you know, AI ethics review or something, because based on this tool, like, I'm not sure that there might be, you know, problems with this data set. And then they could come back to you. Now, hopefully this doesn't devolve into some type of, like, you know, ultra bureaucratic, like, can't allow any progress, agenda driven, you know, sort of nonsense, but stays more as like a science and an engineering and a mathematical and an objective kind of policy, you know, method.
Yeah, I think that's the concern, that it might become a form of gatekeeping, or, you know, there was a clerical...
And it's a legitimate concern.
Yeah, exactly. But by the same token, I mean, no one understands how their computer works. And I mean, I love Kate Crawford. I'd love to get her on the show to talk about her book. But is it reasonable to expect an engineer to be that much of an expert? And then I completely agree with Keith that we should have guardrails and we should have operating frameworks around doing all of this stuff.
And tools.
But no one knows how these bloody models work. Right?
Yeah, it's a big problem.
Well, that gets into the whole, you know, conversation around how to make these things understandable. And there's a line at which I think in one of our videos I said something like, it seems a bit strange that we're building mathematical models to understand mathematical models. You know, we kind of get into this circular problem where the understandable AI feature sets are more difficult to understand.
I know.
Or as difficult to understand as the starting ones. You know.
I know. I made a video on Lyman Schaap with Connor, one of the data scientists at work, and it's almost harder to explain how they work than the underlying model. And anyway, Guy, thank you so much for coming on the podcast. It's been an absolute honor to have you on.
Oh, thank you for
really appreciate
the invitation.
Your time.
Guy,
thank you,
this
Walid.
was a pleasure. I really enjoyed it.
Likewise.
It's an honor to meet you. Okay, guys.
Awesome.
Chat later.
Thanks.